All right, so first thing we want to do is you want to write down the givens. All right, Saidi, give us one of the givens. Okay, so we can write that as d equals 10 meters. You could also write this as like x final equals 10 meters, right? We'll write it as d because that's like the distance we're going to fall, right? So d is 10 meters. What is some more given information based off of the text of the question? Janelle?
Yeah, no.
Oh, we're still working on givens. There's 2 more givens we have to write down. Declan, what do you have? So at time equals 0, at the beginning, there's a given. Something we know about its motion, they tell us right at the beginning. It's not a number, but we can figure out what that number is. Elio? Okay, it's being dropped, yeah. You gotta say it. It's in free fall. Okay, we'll use that in a second. There's something else. Sydney? It's at rest. That's one of those hidden givens. What do we turn that into? What's equal to 0 when it's at rest? It's initial velocity. Being at rest means your velocity equals, it's like just like that's the definition. In physics, if you are at rest, that means at that instant in time, v equals 0. Okay? All right, and now let's use what Yanniset brought up about it being in free fall. What can we take as a given because we're in free fall? Here's my hint. It tells us something about what A is equal to. First, what is A? Acceleration. And what yesterday, both in the video and in the lab, we learned that the acceleration is equal to 9.81 meters per second squared. Okay? Yeah, get that squared. That's right. All right. So what are we trying to solve for? What is our unknown? What does the question want us to figure out, right? The time it takes to fall, right? I think if you don't write these things down first, you're just making your life harder on equation, substitute, and solve. It is not easier to magically come up with the equation by reading it through magical powers and then go back and find the information you need. It just isn't. Not when this is at the beginning of your physics career. 5 months from now, then yeah, maybe you will have gotten enough practice, right? Even myself, I don't solve questions by reading it and go, well, I think I'm going to use this equation and then we'll see what happens. I always think about what is given, what is unknown, right? I really, really want to emphasize that going forward because it's wasting time. If you're not going to get the givens and unknowns first, you're just making your life harder. You're going to get frustrated. And now a homework that takes 15 minutes is taking 30 minutes, and you're not getting the same result out of it. All right, so now that we have our givens and our unknown, which equation do we want to select? You can give me either the equation we started with yesterday or the equation that you take off of the reference table. Do you want to do that for us? Just read off that equation off the reference table. Yeah. Mm-hmm.
D equals velocity, initial velocity, time, plus half acceleration times squared.
Okay. So this is the version of the equation you'd see on the reference table. What's different about this equation from the one yesterday? This one's got an extra piece to it. Makai, what does this equation have that yesterday didn't?
The t squared and the v. No, okay, the v that right there.
This part. Okay. So yeah. So what can we do with that part there? The circled part in red. It's equal to 0. Why is it equal to 0? Because it starts at rest. V initial is 0. And remember, if you multiply two numbers, if one of them is 0, the whole thing is 0. Okay, so now we have d equals 1/2 a t squared. All right, the next thing that I want to talk about is how do you solve this algebraically for the time? At this point, you could put the numbers in with their units and go through the whole process of trying to solve it with all the numbers in. Again, I don't recommend that. I think you're making it harder on yourself if you don't algebraically solve this first. The biggest thing that I saw yesterday, which kind of shocked me, there are lots of people that try to subtract 1/2 from both sides. Yeah, that's how I felt. I was like, what? The rules of math still apply, right? All of these things in the right side are multiplied. So if you want to undo them, we have to do that with division, not with subtraction. Okay? We're taking our math and we're using it to solve physics problems. So let's remember our math. So I divide by 1/2 on both sides, divide by a on both sides. Okay, I'd get 2d over a equals t squared. Again, once I prompted people, a lot of people got to this step. Then what's the trick to get t by itself? Saida? Square root. Okay, and again, that was a thing that started throwing people off. There's like dividing by another 2 or something. I don't really know where that was coming from. The other thing you want to make sure is that you are square rooting both the numerator and the denominator. So you got to be careful in your calculator. That might mean you need to do the division, write that number down, and then take the square root. If that's something you have a hard time with in your calculator, I'll be more than happy to show you with your specific calculator how to do it. All right. Any questions about our just before we substitute, Micaiah?
I did this yesterday, and I was still getting the question wrong.
So the other thing you want to be careful of is about the units. So from yesterday, we needed to make sure we changed the centimeters into meters, right? Before you can do this math part, all of the units have to be the same. Here we don't have to do that step because our distance is in meters and our acceleration is in meters per second squared. But that is something to be aware of. Any other questions before we substitute? Okay, and then the last thing I want to emphasize is that your substituting must include the unit. Okay, I know on the homework it's not always checking up on you on that, but on the exam I definitely will be, right? And the last thing I want to see is come June, you do all of this work and only get half credit because you forgot to write the units when you substituted. Okay, so 2 times 10 to 20 divided by 9.81, and we get what 1.42. So I don't know. That part doesn't matter. We can round it however we want. Let's round it as 1.42. Okay. So what we want to do, any questions about this before we move on? Sadie's like thinking. She's like, what? Talk to me.
When you divided the
Are you concerned about the units? Oh, let's check up on those units. So here's what I'll do. I'm just going to write the units part. I'll leave out the numbers. So I need to do the square root of meters divided by meters per second squared. This turns into multiplying by the reciprocal. So this turns into meters times second squared over meters. The meters cancel, and I take the square root of second squared, and I'm left with seconds. That was awesome. Good question. Okay, that's a way to check if your work even makes sense. Let's say you accidentally multiplied by the acceleration. Now you'd have meters squared over seconds squared, and you take the square root, and now you have an answer of meters per second. You go, oh, that doesn't even make any sense for time. And that's a way to spot your work. It's like a pro level tip. Okay. The units should go into the equation. Yes. Because again, let's say instead of being 10 meters, this was 10 centimeters, right? You would still get 1.42, but the units is no longer seconds, right? So the unit is just as important because the whole measurement requires both the number and the unit. Okay. So what we want to do today, yes, fair. Yeah. So what we want to do today is we're going to take this idea of free fall and we're going to apply it to the more complicated situation of what's called projectile motion. But we're going to do the easiest version of projectile motion today. And then tomorrow, we're going to do some sort of group questions with the online simulation. so that we can sort of get some more experience understanding what projectile motion is. But our goal is to take what we already know about objects that are falling, which we did yesterday, and objects moving horizontally, which we did last week. We're going to try to put it together. So to start, here is Fiegel. Fiegel joined the circus, and Fiegel is going to be a human cannonball now, or I guess a bird cannonball. And so we're going to launch Fiegel horizontally from this cannon. Don't worry, there's like padding here. So when Fiegel hits the ground, he'll be okay. I promise. Plus, I think he can fly. I don't know. I'll have to ask. Oh! Wow, that was perfect. Okay, so here's what I want you to discuss at your table. What are some things that you would want to know about the motion, that path that Fiegel makes when he soars through the air? Okay, so at your table, take 2 minutes, come up with some ideas, and then pick a person and one idea that you're going to share to the whole class. Okay, so you're answering this question in your group, and then we're going to share as a class.
I have one question.
Sure.
Is that the angle where?
So right now he's being launched just like perfectly horizontal. Tomorrow we'll look at when we start changing the angle. Yeah, so Fiegel is being launched perfectly horizontal for today, and then tomorrow we'll look at what if there's an angle. So again, come up with some ideas and then pick one that you'll share with the class. No, you don't have to draw it. You don't have to draw it. We're going to do a different activity on the whiteboards. Yeah, we're still going to use the whiteboards for a later activity. All right, let's take like 10 more seconds to decide on who in the table is going to share. And we're going to start with table number 1.
Could force be a thing? Because you also don't want to launch.
We don't need to worry about force for like what we're going to describe the next 2 days. But you could. You've got the best questions. I mean, we'll talk. Actually, we're going to talk about how that would affect the motion tomorrow. That'll be the last thing we do tomorrow. Okay, so let's start with table number 1. Again, your table is just going to share what is one thing they want to know about the motion. If another table says what you came up with, say, I agree with table, and say their table number. All right, so table 1, get us started. What do you want to know about the motion? Okay, so we might want to know what is the shape of path. Table 2. Table 3.
The distance that he's going to be launched.
Fancy word for that is the range. Table 4. Distance, awesome. Table 5. Okay, so height. Table 6. The height, cool. Table 7. And table 8. Distance, okay? So by the end of class today, we will talk about all of these things, what the shape of the path is, how the time plays a role. We're going to connect that to what we did yesterday, how you can determine the distance or the range, and then again, what effect the height has on all of these things, okay? So we got a great list here, really excited. So to start, let's focus on the path, and then we'll use our skills to be able to describe what that path would look like. So here are a bunch of different options for what the path might look like, right? And I'm gonna give you 1 minute. I just want your table to kind of come to a consensus on which path you think Fiegel will take, and then we'll just put some check marks by it, okay? And then you'll write down what your prediction is in your notes, okay? So you got 1 minute, decide your path, and then draw the path you think in your notes. So D is the one that goes over and then down. So yeah, this is A, B, C, and D. No, no, like this is actually what the path would be. There's no wall, there's not hitting anything. This is just the path. All right, so you got 20 seconds. Again, in your notes, draw the one you think and then decide who in the group is going to share with the class. All right, so we'll go in reverse order this time. So we're gonna start with table 8, and all you have to share is which letter that you think the path will be. All right, so table 8, make a choice. All right, table 7, table 6, table 5, table 4, table 3, table 2, and table 1. Okay. All right, so we're almost evenly split. We got a few more for B's than we do for C's. Okay, and let's see if we can take two ideas and actually prove what the correct shape of this path would be. So what I'd like you to do now is on your whiteboards, we're going to make a motion diagram for the horizontal motion and then for the vertical motion. And then I'll show you how you could take those two motion diagrams and actually draw out what this path would be. So here's what I want you to do. First of just like a 10 seconds of info. So the vertical direction is just like being dropped in free fall, which means it's constant acceleration. And the horizontal direction is constant velocity. And those are the two different types of motion that we have talked about so far, right? And so to start, let's just, so we can have some numbers to help us. Let's say he starts at a height of 11 meters and his initial horizontal velocity is 5 meters per second, right? So that would look something like this, that this initial height is 11 and that this velocity horizontal is 5. So just jot that down on your paper real quick. So that initial height, y initial is 11 and v initial is 5. We're going to do this in 2 stages. We'll spend 4 minutes coming up with the motion diagram and then 4 minutes working on the vertical. So 4 on the horizontal, 4 on the vertical. Okay. So here's what you need to do the horizontal part. So you're going to make a horizontal motion diagram. You need to have 1, 2, 3, 4, 5, 6, 7 dots on it. Okay. This is to get you started. So you need to go from 0 to 9, and your first dot is at t equals 0. So you need to add another 6 dots that show the motion in the horizontal direction. V initial is 5 meters per second. Okay, so you got 4 minutes for this motion diagram, and put it in a spot on your board so you don't have to erase it when we do the second one. Okay. Okay, so it starts at 0, right? That's my hint to get you started. So think about how far it should move every second and how you can figure out where it's located at these other times. This tells you how far it goes every second that goes by.
Oh, so you're supposed to use this.
Well, and then what would the A be? Exactly. So you would say, so you would draw this, and you're going to put dots. It's just 0. You don't have to write it down. So yeah, my hint is at t equals 0, at 0 seconds, it's at 0 meters. All right, and my other hint is at 1 second, it's going to be at 5 meters. Can you see why? Why would it be at 5 meters after 1 second? And at 1 second, it would be at 5 meters. Can you see why? Don't get too worried about putting it in the exact right place. I know there's some decimals that will come up. If it's at 5 after 1 second, where would it be after half a second? I've got an equation on the board that can help you figure out the exact values. You can use the calculators at the table to help you do these calculations. Mm-hmm. Yes. This room with the rows, you can't even breathe in it. There's like no way to move around. Like the desks go all the way to the teacher's desk if this room is in rows. Unfortunately. That's what I'm saying. You should go to the student town halls and tell Mr. Blank. You'd be surprised what he'd do if a student asked for it. All right. So take a pause from that. Okay. We'll go over what it looks like in a second. But now I want us to change over and think about what the motion would be like in the vertical direction. Okay. So here's your starter at 0 seconds. It should be at 11 meters above the ground. The math on this one's a little bit trickier. Okay. So I'm just going to get you started with the formula right away. Okay. Using this formula, you can figure out where it is located at all the values of time. Okay, so you're going to have to plug in each of these values of time into this formula in order to get them. All right, so I'll give you 4 minutes. This one's a little bit trickier, but you need to use the calculator. You need to do the calculation in order to help you. Yes, it is. Right, so you can see the similarities to our formula from before. What's that? You want to try it out? Sure. Again, I'm not so concerned about what the exact numbers are, but we're trying to get the shape. How do the dot spacing, how does that change as time goes by? And I'll give you one for free. At 1.5 seconds, it's at 0. So the last one, 1.5 seconds, it's at 0. Yes. So the next dot, so if you do, like, let's plug in 1 second. Let's do that one. So 11 minus 0.5 times 9.81 times 1 squared. Okay, so that means when t equals 1, it's located at 6. Oh, no, over here, I'm sorry, at 6. And and these dots just go along this axis, and then these dots go along that one. And then together we'll show how they tell us where it's located in the middle. So your dots should just go along the number line. Okay, so your dots just go along the number line. And again, I'll give you another one. So when t equals 1.5, we're at 0. And when t equals 1, we're at 6. So get a couple more on there so you can see the pattern. It's about another minute. Again, how does the spacing change as time goes on? You've seen this pattern before.
When you're doing this, do you bring over the 2 to the other side? Because
No, you would, so this is 11, and this is 9.81, and you just put in the different, you put in 0, 0.25, 0.5, 0.75. Because this is what we want to know. We want to know where is it at the time you plugged in. 11, because that's where it starts when t equals 0. Whatever, so if you put in 0, you put in 1, you put in 1.5, and it tells you where you're located. All right, 20 more seconds. Again, look to see if you can spot the pattern, what's happening to the spacing between the dots as time goes on. Again, this is a motion diagram we have seen before. All right, so let's take these two different motion diagrams, right? And let's start putting them together. So first, what I've done is I've taken my x and my y and I've put them next to each other, right? One in the x direction, one in the y direction. And for the vertical motion, this is what I got. Okay. What's happening to the spacing between the motion dots as time goes on? That spacing is increasing. Why was that spacing increasing? What kind of motion is happening in the vertical direction? Yeah, I said. Free fall. It's acceleration, right? So if we went down another quarter of a second, that spacing should be even larger. Okay. In the horizontal direction, and lots of tables had this, I end up with something that looks like this. Okay. Again, what's going on with the spacing here? It's a constant spacing. And why is it a constant spacing? Because the velocity is constant, which means the acceleration is equal to 0. Okay. Now here's how we would put these together to get the shape. What I have to do is think about the y position along the y number line and the x position along the x number line. So at 0 seconds, well, we're at 0 in the x and 11 in the y. So I'll just put up a little blue dot there. Right? Then I go to 0.25. Well, I've gone down a little bit vertically, got a little bit to the right horizontally, and here's another blue dot, and another one, and another, and another, and another, and I end up with the actual path that the object takes. So which shape was this? It is B, okay? Yeah, I know. I had a really hard time trying to draw a parabola in PowerPoint, so I just turned it into a graph. Had to do what I had to do. So yeah, that is the shape of this graph. It is a parabola. Oftentimes, common misconception, and it's why I have Wile E. Coyote here, right? Is this idea that like somehow the gravity doesn't start to happen until, I don't know, like a later time, right? So that path, or it just went straight across and fell. No, it's in free fall the entire time, right? And that is also true for path C, right? Where it was kind of in the right shape, but then at the very end, it just stopped going horizontally and just went straight down. It's constantly moving in both directions, right? And that's how we end up with the problem. So here's what I want you to think about in your groups. How could we get this horizontally launched projectile to be in the air for more time? Okay, what things can you change, or could you maybe not change, that would result in that? So take a minute, come up with some ideas, and then we'll do a share around the room again. What could you vary so it stays in the air for more time? Think about what we just saw about the motion. How could you make it stay in the air for more time? All right, so decide on who's going to share. You got 5 seconds. All right, so table 1, what do you want to vary so that the projectile remains in the air for more time? Height's fine. You can just one answer is fine. Table 2, what do you want to vary so it stays in the air for more time? The angle? Table 3?
Force.
Table 4? Table 5? Table 6? Table 7? And table 8? Okay. So the first thing I want to point out is, yes, varying the angle, if we aimed it up, would definitely increase the time, but we're limiting ourselves to where we don't get to change the angle. Okay, so that's a correct answer, but we're just going to focus on other things for right now. We'll talk about the angle tomorrow. The second thing is this idea of force. Once we're in free fall, the only force acting on is gravity. Right? We're going to talk more about that in our next unit. So the force itself would have no effect. But I think I know what you want to say to me. You want to change what the speed is. Does the speed affect how much time it's in the air? It does not. We are in free fall the whole time. And it does not matter if it is also moving horizontally at the same time. The free fall part is just determined by the height. You want your projectile to be in the air for more time, push it off a higher cliff. Or as we'll see tomorrow, you can launch it vertically, but for right now, all we can vary is the height. Here's a related question. What if you want it to go farther? So same thing, discussion in groups, you got a minute. What can you vary so it goes a longer distance? No. Not for how much time it's in the air. I will show a video. We have the demonstration somewhere. I just don't have all the right equipment to do it. But it's this thing that takes a marble and it drops it and pushes it to the side at the exact same time, and then you hear them hit the ground at the same time. So the horizontal part of the motion is independent from the vertical part. Mythbusters did an episode about like, is a bullet fired from a gun, does it hit the ground at the same time as one that's dropped? And they did like slow motion video and showed that it does. It's like just like how it's really fascinating. Yeah. All right. So let's just hear from maybe one or two groups on this one. We'll go around the room. Let's start with table 8. Okay. Table 7. Table 6. Table 5. Table 4. Table 3. Table 2. Okay. And table 1. Force. Okay. There's one that's missing. Yeah, not only does the speed affect how far it goes, but also the height. Right? Why does the height also affect how far it goes? What does increasing the height do? You ready? Yeah, but what does it change? Mantis, what does it change? It changes the distance. Think about how we figure out the distance. We care about the speed, but we also care about the time, right? So increasing the height makes you stay in the air for more time, right? If I asked you to jump as far as you could, right? If you jumped off of something that was higher up, you'd be able to jump farther than if you jumped from where you were standing. Okay? So it's two things, both the height and the speed. So here's what the last thing I'd like you to do is I want you to complete these 3 sentences in your notes. They summarize what we did today. Okay? So you can work together. You've got 2 minutes to write them in your notes. They all start the same. They just have because, but, and so in them. And they summarize what we did today. No, this is for your notes. All right, so you got 2 minutes, and this summarizes today's class. And we'll continue looking at this tomorrow. Right, all the things you were talking about, all those examples of force, we will clear up what all of that stuff means in our next unit. All right, so finish up the last thing you're writing. It's the end of the period.